Like feel down. I think like the color works like whatever. After getting things, I heard that we never get together for good reason. We never get together. But my dad's side, we get together. So it's half of us, like half of us to New York. I think it's what I'm going to do. They're really smart. Like you're studying. It makes me sad. I know. It's not like French. Oh, did you? I know it's over with friends at 24. So like when it goes into the probably take them off. So but now like these things in college it's going to be super fresh in college and hard. It just feels like now. It's weird. The oldest and so like words is there's basically one of us are born per year for 8 or 9 a month. So it's so big. It's just it's only 1 year. That basically connects to this time. My home language.
Okay, let's go. Let's turn to page 21. So we've explored a little bit with inverse functions, but so far we've seen logs and exponential function e to the x, that they're inverses of each other. And now we're going to talk about inverse functions of trig. We don't have to worry about what the graph looks like. We just to be able to find the derivative. So that's just something that we don't have to worry about with the graphing. So, just a little bit of review here. So none of the 6 trig functions is one-to-one, meaning that if we were to basically take a sine or cosine and flip it on the side, it turns into its inverse, but it doesn't stay as a function because it wouldn't pass the vertical line test. So imagine taking a sine function and flipping it on its side, it would start looking like S shapes and it wouldn't pass the vertical line test. But if we were to, meaning that it wouldn't be a function by itself unless we restricted the domain. So if we were to say that, okay, this inverse sine has to start and end at a certain point so that it doesn't cross over itself, then we can technically call it a function. So arcsine and sine are inverse functions of each other. What that means is that if we were to take the inverse, function, plug it into the function, or vice versa, they're going to cancel each other out, leaving us with just x. So arcsine of sine is equal to x, and the sine of arcsine is equal to x. And we've seen that with function and its inverse, that they're going to cancel each other out, like natural log and e to the x, right? If I were to plug e to the x into natural log, I'm going to get them to cancel out with just x. Meanwhile, if I were to plug natural log into exponential function e to the x, I'm going to also get them to cancel out. So it kind of has that similar relationship in the sense that a function and its inverse are going to kind of undo each other. We have a couple of different notations for inverse sine or arcsine. So you may see this notation arcsine, arctrig, or arctangent, cosecant. You may also see this this -1 notation. We just call it inverse sine. So these are interchangeable. So sometimes you may see notations with this form. Sometimes you may see a notation in this form. So just be aware that that they mean the same thing. There's 2 different ways of writing it. So there are 6 different rules that we're going to have to be responsible for. It looks like it looks pretty intimidating, but really it's just 3 rules because the ones across from each other are just the same rules, just negative versions of each other. So arcsine, arc cosine are essentially the same. Arc tangent, arc cotangent are essentially the same. Arc secant, arc cosecant are the same. So we really just have to worry about learning 3 new rules and knowing what the negative versions of them are from these original 3. Before we get to the calculus, we're going to review some algebra 2 calculus topics here. Being able to evaluate just be able to evaluate something that is in the form of a function or a trig with an arc trig inside of it. So let's look at some of these examples. It says number 1 says find the tangent of arc cosine of root 2 over 2. So what that means is that we want to find the tangent of the angle whose cosine is root 2 over 2. So whenever you see this messy notation, just understand that this whole thing represents theta. Right. So what we're going to do is we're going to draw a triangle and label the angle theta and build out a triangle with this property. Okay. So arc cosine root 2 over 2, what this means is another way of saying when is cosine of theta equal to root 2 over 2. So anytime we see this arc trig notation, we can always rephrase it in a way that feels more familiar. So what we're going to do is we're going to draw a triangle and label the angle theta, which we're going to do here. We're going to label the sides according to that arc cosine given. So if cosine of theta is equal to root 2 over 2, we know cosine is adjacent over hypotenuse. So we can say adjacent over hypotenuse. I can use the Pythagorean theorem to figure out that third missing side, a squared plus b squared equals c squared. And then if I do this here, root 2 squared plus b squared equals c squared. I get 4 minus 2 is 2, so b squared equals 2, therefore b is square root of 2. So using Pythagorean theorem, we can find that third missing side. And now that we have that side figured out, we have a triangle that we can finally go back and say, okay, now that we have the triangle filled out, we're now going to ask, what is the tangent of theta for this scenario? So therefore, tangent of theta will just be opposite over adjacent. So root 2 over root 2, therefore equal to. Number 2, find the cosine of arcsine of 5 over 13. So understand this whole thing represents theta. Another way of thinking about what that inside portion is doing, we're going to create a triangle where sine of theta is equal to 5 over 13. So now that we have a triangle with theta filled in, let's see where that 5 and 13 can go. So sine is opposite over hypotenuse. So 5 over 13. Pythagorean theorem, a squared plus b squared equals c squared. We get 169 minus 25 is 144. Therefore, a is square root of 144, which is 12. Now that we have the triangle filled in, we can turn around and ask, okay, what we really want to know is what is the cosine of theta? And cosine of theta is adjacent over hypotenuse. So therefore 12 over 15. Okay, next page. Now, in the same way, we can also do this type of scenario when there is variables involved. Okay. So example 3, write the expression secant of arc tangent of 3x in algebraic form. So much the same way, understand that whatever is inside that set of bracket represents theta. And if we say theta is equal to arc tangent 3x, that's another way of saying tangent, let's create a triangle where tangent of theta is equal to 3x. I'm going to force a 1 in the denominator because I want to see where my ratio portions are going to be. So anytime we're dealing with the trig, we always like to have a fraction so we can kind of clearly see, okay, that's my, in this case, opposite, and this is my adjacent. Right? Okay, so we're going to create a triangle with these sides filled in. So tangent of theta, we will create a situation where tangent of theta is 3x over 1. So tangent is opposite over adjacent. So we'll let 3x be the opposite. We'll let 1 be the adjacent. So even though we don't have numeric values here, we can still go through Pythagorean theorem and find the missing sides. So a squared plus b squared equals c squared. Notice that we're squaring not only the x, but also the 3 as well. So leaving that in a set of parentheses. So therefore, 1 plus 9x squared is equal to c squared. We take the square root, and that's going to be our hypotenuse, square root of 1 plus 9x squared. Now that we have all sides of the right triangle filled out, we can turn around and ask what we're really looking for, which is secant of theta. So secant is related to cosine. Cosine is adjacent over hypotenuse, so therefore secant will be the reciprocal of that, hypotenuse over adjacent. So secant of theta is therefore going to be root 1 plus 9x squared over 1, which is really root 1 plus 9x squared. Okay, we'll get some more practice with some of these algebraic skills a little bit later. Let's introduce the derivative rules now. There's actually 2 ways of doing this. There's a way of using implicit method. I'm not going to show this way. I feel like this is a way that allows us to avoid having to memorize these rules, but it also takes a long time. And when you have a problem where you have product rule, chain rule involved, it just takes too long to have to go through this other method. So, but it's a good review with implicit. I'm just going to move into talking about the derivative rules. Okay, let me just show examples 5 and 6 in terms of applying these rules, and then I'll talk about how I go about memorizing these rules here. So if we look at the top of the page here, we have the 6 derivative rules involving trig. arc trig. And if we want to find the derivative for arc tangent of 4x, then we look at the rule here. Arc tangent of u is simply u prime over 1 plus u squared. Now, the u is whatever is inside the parentheses. In this case, will be the 4x. So we just simply follow what the rule says. U prime over 1 plus u squared should be pretty straightforward. So y prime is equal to 4x becomes 4. That's my u prime. And then my 1 plus u squared is 1 plus. Now, make sure that we're squaring everything inside the u value. So not just the x gets squared. The 4 also gets squared. So our derivative slope formula for whatever this graph looks like will be spelled out by this 4 over 1 plus 16x squared. So if I want to find the slope of any point on this original graph, I just give it the x value, and I can pinpoint the exact steepness of this graph. So my y prime, my slope formula is simply 4 over 1 plus 16x squared. Okay, example 6, find y prime for y equals 2 arc secant of 3x squared. So if we look at arc secant, it's the most complicated looking rule here. It's got the u prime in the numerator, just like with arctangent, but the denominator is absolute value of u times the square root of u squared minus 1. So we just have to be able to fill in u prime, u values to get to the derivative. So I'll write the rule here so we can just apply it. Now the 2 is going to stay. That's just the coefficient. So my 2 is going to stay times whatever's inside the parentheses. That's my u value. So my u prime is just going to be 6x. Absolute value of u. So we put absolute value of 3x squared. Square root of u squared minus 1. So make sure we square the entire parentheses. Now, as far as cleanup, we can cancel out between, what's inside the square absolute value can cancel out. It's just that if there's any x left over, we need to leave the absolute value there. So we got 12 over 3. That could cancel out to be just 4 up top. One of the x's can cancel out as well. So we're just left with 12 over 3 is 4 up in the numerator. There's an x left over inside the absolute value. And then 9x to the 4th minus 1. That's my derivative for whatever this curve looks like. Example 7. Find y prime for y equals x times arc cosine of 2x. Now, hopefully we see that there's a need for more than just arc cosine, right? What do you notice here? What rule do we have to involve? Product rule, yeah. X is a separate function that's being multiplied with arc cosine of 2x. We got to go through product rule here. Okay, so f prime g plus fg prime. Now, arc cosine looks a lot like arc sine. It's just the negative version of arc sine. So at the very top of the page here, we're just going to apply that rule when we get to it within our product rule. So u prime over root 1 minus u squared with a negative attached. So x becomes 1. G stays as arc cosine of 2x. back to f, so x stays. And then our cosine is negative u prime over square root of 1 minus u squared. So negative 2 over square root of 1 minus quantity 2x squared. Okay, do a little bit of cleanup here. I can merge, I'm going to merge this to one fraction, but I can just keep that separate here. Y prime equals arc cosine of 2x minus 2x over square root of 1 minus 4x squared. Example 8, find y prime for cosine of arc tangent of x. What do you think we have to go through here to find the derivative? It's a function within a function, so what rule can we use? Chain rule, right? Okay, so we can take care of cosine's derivative first. And once we're done with cosine's derivative, we can go inside and deal with arctangent's derivative and let that take its course. So cosine's derivative, y prime. Cosine becomes negative sine. Times. So we took care of the outside derivative. So let me just make sure we start with that. And that there's an outside, inside portion that we're taking turns doing. So cosine's derivative is negative sine of u, negative sine of u times u prime, and that u prime is where that arctangent gets impacted. So arctangent derivative is u prime over 1 plus u squared. My u value is x, so 1 over 1 plus x squared. Now we can actually go a little further with cleanup in the sense that whenever we have a trig with the inverse trig inside, we should be able to go through this process and get it in terms of just x. So we're going to kind of step to the side and deal with that process here, get this in terms of x, and then we can merge that together. So arctangent of x, we know that is representing theta there. So I'm going to create a triangle. This is basically saying, let's create a scenario where tangent of theta is equal to x over 1. So tangent is opposite over adjacent. Pythagorean theorem, a squared plus b squared equals c squared. 1 squared plus x squared equals c squared. So 1 plus x squared with the square roots, because we have to take the square roots with that c squared. And now we can turn around and figure out what we really want, which is sine of my theta. So sine is opposite over hypotenuse with a negative in front. So y prime is equal to opposite with a negative in front over root x squared plus 1. Opposite over hypotenuse, and then fill out the rest of what we have already, 1 over 1 plus x squared. This is fine, but we can just want to show you that we can actually combine this a little further. This is x squared plus 1 to the 1/2. This is x squared plus 1 to the 1. They're both the same base. I can just add the exponents if I want to multiply this. So 1 plus 1/2 is 3/2. Okay, I want to talk about working towards memorizing these derivative rules. So if you can turn to page 27, there's a blank page there. I just want to kind of talk about the process I go through in terms of remembering these rules. So much the same way that I like to organize my trig functions. I'm going to organize my arc trig functions the same way. I will have the sine, tangent, secant on the first row, and the second row are going to be the C functions in alphabetical order, but arc cosine, arc cotangent, arc cosecant. So I'm going to write them in this order here. So much the same way that we've done with trig, but we're just putting arc in front of these trig functions here. So just like with trig functions, all these are going to be the negative versions, the negative derivatives as well, just like with the original 6 trig functions. So we're just working on these 3 here. These are really the 3 that are unique, and then these are just the negative versions of the ones next to them. So arc sine, arc tangent, arc secant. The similarity is that if we look at these rules here, they all have u prime in the numerator. So that's nice. That's similar. What's different is the denominator, right? One doesn't have a square root. 2 of them does. But if you look in terms of similarity, they all are involving 1 and u squared in the denominator. So this is the way I go about doing it. I know that all my numerator has u prime. So I start off with that. That's all going to be the same. Our tangent is the simplest, or the simplest looking denominator. It doesn't have a square root, doesn't have absolute value, it doesn't have a minus sign. It's just 1 plus u squared, or u squared plus 1. It doesn't really matter the order. So I like to start there. Next up, I'm going to fill out the most complicated one, which is the arcsecant. And this is going to help me with my arcsines. Arcsecant is the most complicated looking one because it's got the absolute value. It's got another set of square roots. So we have absolute value of u times the square root of, and it's also involving 1 and u squared, but it has a certain order here. It's going to be u squared minus 1. Right. Now, what helps me remember the order, what's inside that square root, is I know that the u's are next to each other. So that helps me, kind of gives me a little bit of reminder there. Okay, I know the u's are next to each other. So that helps me remember, okay, it's u squared minus 1 and not 1 minus u squared. And now if I have this in front of me, it's a lot easier to figure out what arcsine is, because arcsine is similar looking to arcsecant. It's got the square root, it's got the 1, it's got the u squared, no absolute value, but I know if I can figure out the order here, I know the order is going to be slightly different with arcsine. So because this is u squared minus 1, I know arcsine is going to be 1 minus u squared. So that's how I go about building out my derivative rules there, starting with the similarities and then filling out the differences. So if I can have these 3 filled out, then these 3, I can just copy what I have next to it and just put a negative in front of each of the derivatives. Our classwork / homework is just going to be page 23. So I think within the next 5-10 minutes, we should be able to finish it all in class. So let's go ahead and try that. The key is attached on page 25. So you guys can check your answers, but let's start off with page 23. So just page 23, the top half is just evaluating expression, and the bottom half, I'm sorry, so this is all just going to be algebraic review here. No calc. We'll save the derivative homework for tomorrow. So just page 23. You're evaluating an expression with numeric values, and then you're evaluating involving variables there at the bottom. Yes.